Hello everyone, this is Professor Ng Chi Kun from Unimas. Today I'm going to give you a tutorial solution on a question on approximate analysis of statically indeterminate frame with vertical loads. In this particular tutorial question, we are asked to determine approximately the internal moments at joints A and B of this particular frame. So this frame has got 3 bays of 6 meters, 8 meters and 6 meters, and the girdle is subjected to a 3 kilonewton per meter length uniformly distributed load. So to begin, we use the 3 assumptions that we make for the analysis of frames using the approximate analysis. So first of all, the hinges or zero moment points or the inflection points occurs at 0.1 L from the supports on each of the segments of the girder. So with that, we can simplify the structures, or we model the structures in this manner, where we have 3 simply supported beams. Each of it is having a span of 0.8 L. So this total span is 6 meters. So 0.8 times 6 is 4.8 meters for this simply supported beam. For this simply supported beam here, we have 0.8 times 8 meters, so 6.4 meters, and then this is similar to this side. So each of these distances are 0.1 L, 0.1 L, 0.1 L, and 0.1 L. So in this particular tutorial question, we are asked to determine what is the moment here at joint A, the internal moment at joint A, and also the internal moment at joint B. So in this case, we're going for joint A moment, we're going to take this beam as a free body diagram and analyze it for its support reactions, and the support reactions will become an action on the cantilever part of the girder. So in this case, we can model this as a free body diagram as well. So if we take this beam and this part of the structure as 2 free body diagrams, then they will look like this. This is the beam part, and this is the frame with the cantilever girder part. So to solve for the simply supported beam part, let's look at the free body diagram. Let's look at this free body diagram first. So this beam has a span of 4.8 meters and is subjected to a 3 kilonewton per meter length uniform load. So this uniform load, when we convert it to a resultant force, is 3 kilonewton per meter length times 4.8 meter span. So the resultant we have got is 3 times 4.8, and the unit is in kilonewton. So this beam is symmetrical in loading and in support conditions. So we said that each of these support carries half of the total load. So the total load is 3 times 4.8. So each of these will be half of 3 times 4.8, which is 7.2 kilonewton. So these support reactions, because this beam is sitting on this part of the structure, so this support reaction is provided by this part of the structure. So these support reactions become an action on this part of the structure. So we have a downward force here arising from the reactions here. So this is also according to Newton's third law. So whenever you have a reaction, there will be an action. So these two forces here, they are complementary to each other. So one is reaction, the other one is action. And then on this small length of structures here, which is 0.6 meters here, we also have the uniformly distributed load of 3 kilonewton per meter length. So in this case, we have a uniform load here which is 3 kilonewton per meter length, and the resultant is 3 kilonewton per meter length times 0.6 meters, which is this. So this unit should be in kilonewton, not meters. Okay, there's a mistake in this diagram here. So this should be taken as kilonewton. So this force that we have arising from the uniformly distributed load is 3 times 0.6, which is 1.8 kilonewton. Okay, and then the distance is half of the total length where the uniformly distributed load is acting. So it's 0.3 meter to this 1.8 kilonewton force. So now we have already detached the support of the frame here. So we have to put in the reactions. So for a fixed end here, supposedly there should be 3 reactions. So there should be another horizontal reaction. But in our assumption, we say that the girders are not subjected to any axial force. So there is no horizontal reactions in the girders, and therefore there is no horizontal force also in the reaction. So meaning that this reaction is not there, so we can ignore it, and it's also be considered to equal to 0. So we don't have to consider the horizontal reaction here. So now we can start to sum moment about joint A or point A. So now we want to sum moment about point A here. So moment about point A, we have internal moments in the column here at the support, which is MA, and then this vertical reaction AY is passing through joint A, so this force here does not produce any moment about joint A, and then this force of 1.8 kilonewton is having a moment arm of 0.3 meter about joint A, and this 7.2 kilonewton force is having a moment arm of 0.6 meters about joint A. So we will sum moments of MA, this 1.8 kilonewton force and this 7.2 kilonewton force. So in this case, we sum moment at joint A, and then it should be equal to 0, and then we take anti-clockwise moment as positive. So this direction of MA is assumed in the first place. So MA is assumed to be anti-clockwise. So MA, we have a positive sign. And then we look at 7.2 kilonewton force first. So 7.2 kilonewton force has a moment arm of 0.6 meters to joint A, or point A. So this force will produce a clockwise moment about joint A. So clockwise moment, we take it as negative. So 7.2 times 0.6 meter, which is the moment arm. And then for this 1.8 kilonewton force is 3.3 times 0.6, is having a moment arm of 0.3 meters, and then it produces clockwise moment about joint A as well. So clockwise moment is negative. So negative 1.8 times 0.3 meters. So there is no other moment or force that causes moment about joint A, so we equate this to 0. So solving for MA, we have MA equals to 4.86 kilonewton meter. So the solution is positive, meaning that the direction of MA in anti-clockwise direction that we assume in the first place is correct. So MA is an anti-clockwise moment at joint A. So that is part of the solution. So this is the internal moment at point A. So now we have to move on to the next solution, which is a moment at point B. So moment at point B, we have this beam that is sitting on the part of the structure that is related to point B, and we have this part of the beam that is also related to the solution of moments for point B. So in this case, we have to take this part of the beam, and then we have to take this part of the beam as well, and then this part of the structures for the solution of moment at point B. So what we get is something like this. So this is the simply supported beam of 4.8 meters, and this is the simply supported beam of 6.4 meters. And each of these beam is subjected to 3 kilonewton per meter length of uniformly distributed load. So we have already done the reactions for this beam. So this reaction is 7.2 kilonewton as the solution before. And then for this 6.4 meter beam, we need to look at the UDL first. So UDL is 3 kilonewton per meter length. So the resultant force from the UDL acting on 6.4 meters is 3 kilonewton per meter length times 6.4 meters. So this resultant force is 3 times 6.4 kilonewton. And then this beam is symmetrical, so the reactions must be symmetrical as well. So each of these reaction is half of 3 times 6.4, so it's 9.6 kilonewton. So this is 9.6 kilonewton, this is also 9.6 kilonewton. So as mentioned before, this part of the beam is sitting on this part of the structure. So this reaction is actually provided by this part of the structures. So this reaction will become an action on this structure. So this is 7.2 kilonewton. And then this part of the beam is sitting on this structure at this location. So meaning that this part of the structure has to provide the reaction of 9.6 kilonewton. So therefore this 9.6 kilonewton becomes the action on this part of the structure. As I mentioned before, reaction and action, they are complementary to each other. And then don't forget that there is a uniformly distributed load also on this part of the structures. So the length is 0.6 meter plus 0.8 meters, so it's 1.4 meters in total. And then the UDL is 3 kilonewton per meter length. So the resultant force is 3 kilonewton per meter length times 1.4 meters. So the magnitude is 3 kilonewton per meter length times 1.4 meters. So this will give you 3 times 1.4 kilonewton. And then the location of this resultant force from the UDL should be at the middle of 1.4 meters. So it should be 0.7 meters if we measure from the left. So this should be 0.7 meter from here to here. But this one from here to here is 0.6 meters. So meaning that from the resultant force of 3 times 1.4 kilonewton is 0.1 meter to the center of this column here. Okay, so after we've got all the forces acting on this free body diagram, including the reactions, so these are the reactions at the support B. So B is a fixed support, so it has internal moment. It also has a vertical reaction, and originally there should be a horizontal reaction as well, but this horizontal reaction is assumed to be 0, so we can ignore that. So we don't need to include the horizontal reaction. So now we can start summing moments at joint B. So joint B, when we sum moment at joint B, we look at all the moments and forces that may produce moment at joint B. Yeah? So this reaction By passes through joint B, so it does not produce any moment about joint B. And then when we sum moment at joint B, we assume anticlockwise moment as positive. So when we sum moment, any anticlockwise moment will be positive, any clockwise moment will be negative. So this direction of MB is not known in the first place, so we just assume that it is anticlockwise. Later on, the solution will tell us the correct direction. And then we have all the forces acting on this part of the structures. So we have 7.2 kilonewton here at 0.6 meters away from joint B. And then we have this 3 times 1.4 kilonewton at 0.1 meter away from joint B. And we also have this 9.6 kilonewton force at 0.8 meter away from joint B. So we have to look at the moment created by these forces one by one. So first of all, we have MB. So we assume it to be anticlockwise, so it's a positive MB according to this positive direction for anticlockwise moment. And then the second force that we look at is this 9.6 kilonewton force. So this 9.6 kilonewton force has a moment arm of 0.8 meter to joint B. And then this force will produce a clockwise moment about joint B. So it will turn this way, clockwise. So clockwise moment, we take it as minus, negative. Okay, so 9.6 times the moment arm of 0.8 meters. And then the next force that we look at is this 3 times 1.4 kilonewton. So this 3 times 1.4 kilonewton force has a moment arm of 0.1 meter, and then it produces a clockwise moment about joint B. So it's a negative moment of 3 times 1.4. This is the force, and this is the moment arm of 0.1 meter. And then the next force that we look at is this 7.2 kilonewton force, which has a moment arm of 0.6 meters to joint B. So this force will produce an anti-clockwise moment about joint B. So anti-clockwise moment is positive, 7.2 times the moment arm of 0.6 meters. So there is no other moment or forces produces moment about joint B. So we equate this to 0. And solving for this MB here, we get MB equals to 3.78 kilonewton meter, and we get a positive solution. But this positive solution means that the assumption of this direction is correct. So MB is an anti-clockwise moment. So with that, we have already got the solution of M, A, and MB, which answers the tutorial question. That's all for now. Thank you very much for watching.